So today we're going over the fundamental theorem of calculus. And in the do now, you had a diagram to draw. So I'm going to redraw it here. Or perhaps this is the time in which you're up to the diagram. So we're looking at the coordinate plane. And we're looking at f, and it's bounded between when x is equal to a and some other value. Beyond that, we're going to call x. Okay, we're now referring it to b. And the reason for that is because when we're finding the area under the curve, or the area bounded from f to the x-axis, okay, we can call this region capital F of x. It's a function depending on what x is, okay? And this is defined as the area under the curve from a to x for some function. So I'm actually going to call the function f of t dt. The reason for this, even though the x-axis is still an x-axis, is because we need x to represent the value we're going up to. And that changes, so that needs to still be the variable. We need this to be x. But we can't make this x as well. So I may have mentioned before about a dummy variable. That means that it doesn't matter what the variable is here or here, just f is represented. And that's why in the diagrams a lot of times I'm just drawing an f. I'm not saying like f of x. So the t could be the values along the x-axis, but it doesn't matter. It could be t, it could be u, it could be v, it could be f, it could be c, it could be s. So the reason for that is so we can do what is called the fundamental theorem of calculus part 1. Okay, there is a part 2. I am not making it up myself. These aren't my designated parts. It's just that there's a lot to learn about the fundamental theorem of calculus. Okay? So I'm going to just say this. Okay, it's really important that we understand something we've learned all the way back in the past in several different courses, and that's something about inverses. So let's say y equals x cubed, and y equals the cubic root of x. These are inverses. Okay. So that means if you do a composition of them one way or the other, so if I take the cubic root of x and I plug it into x cubed, I'm getting x. What students say is that one undoes the other. I'm not even sure if that's grammatically correct, but I like when students can make that association because they understand what they're talking about when they discuss it to one another. And I'm just going to use that so you can understand what's going on over here. Okay? So we learned derivatives, and we just started looking at integration. And from the do now, this is the notation of my integration form. They are inverses, so you should be copying this part down, okay, into your notebooks. And it's saying that integration and differentiation are inverses of each other. So what that means, if they are indeed inverses, if I take this and plug it into the derivative, I take the derivative of that, I'll write out the whole notation, then you're getting f of x. One undoes the other. It's the x that we're getting just like we did before. Okay? One undoes the other, or vice versa. Okay? So that is why we're getting this right here. And this is the fundamental theorem of calculus part 1. Okay? Now, f has to be a continuous function, okay, and it is a derivative of some other function. And for every continuous function f, there's another function, we're just going to call it capital F, whose derivative is the lowercase f. And that's why we had explained this or seen this in the do now. Okay? So the reason why f has to be a continuous function, every continuous function has an antiderivative. Okay, that means it can be integrated. And that's the association. Sometimes we even say find the integral, or it's just like, hey guys, can you find the antiderivative of? And it means the same thing. Okay, and that's why it's actually called an antiderivative. I didn't mean to cross it out. I meant to underline it. Let me try that again. Different color. No? All right, you get it. So, okay, hopefully you understand at this point, if they do undo each other, we get f of x. And that we do understand from the diagram before why this is a statement we can say. And we say capital F of x is an antiderivative. It's not the antiderivative, okay? Because, well, we're going to get to that a little bit later, okay? That just means that it's not the actual answer, it's an answer. It's a possible answer. So let's get to an example, and we can talk about that a little bit, all right? We do have 2 examples, and the second one is actually on the second slide, so let's just take a look at the first one. We want to find dy over dx, so it means we need to take a derivative. We're going to take the derivative on both sides of the equation that you see here. So if I take the derivative with respect to x on the left side of my equation, I do indeed get the dy over dx I was looking for. If I take the derivative on the right side of the equation, okay, it's not written as a function notation. It's telling me what the function is. So what we do, as long as this is the constant, this has to be a, we're going to replace the function with the x we have here. This undoes each other. So remember, you're supposed to get a function of x. So we end up getting x squared. That is our function of x. And we're done. Okay? As we're saying students do, they say they kind of undo each other. Maybe you like to cancel it out. That doesn't bother me, but basically that's all we need to do. And we're done. That's example 1. Okay, so take the derivative of the left side, like always. Take the derivative right side, and that's using our new rule, the fundamental theorem of calculus part 1, and you're done. So now you may be wondering, what if that isn't a constant, that isn't a? Let's say that's a variable just as much as this is, or maybe the constant's up there. Well, then the properties of integrals are going to come into play. So that's why we have example 2 to address both those issues. Okay, so as you're copying down example 2, you're going to notice that what I gave you does have those 2 variations. Okay, the lower limit of integration has a variable in it, and the upper limit of integration, it too has a variable. Okay, we don't see that there's a constant there, but we're going to see how it does have those 2 variations. All right, so hopefully you had enough time to copy this down. So the first thing we're going to do, if we're trying to find dy over dx, is to take the derivative on both sides of the equation with respect to x. So now, in this case, step 2, we do have dy over dx, but now on the right-hand side, because we don't have the constant there, what we need to do is break it up so we can see a constant, and that means that we need to use the properties where we break it up into 2 integrals. Okay, so I'm going to need to keep the d over dx, okay, either on the outside of my 2 integrals, or I can do this in 2 steps or 1. Put it in front of each integral. Okay, so I'm going to keep the lower limit here and the upper limit there. And what I'm going to have between them is where it breaks off. Now, I don't know where that is, but that's where I'm going to write a constant. So I'm using the a. Remember, this wasn't a. We're going to use an a or b or c, whatever variable you want to indicate the constant, okay? It's usually those letters. And I'm just going to rewrite my function here. We're going to try to squeeze it in, don't forget the dt. Okay, and we're off to our next step. Okay, let me just fill in what I wrote above. All right, so next color, green. So what we're going to now do is look at each integral. We can evaluate this because now we have a in our lower limit of integration, but we don't have it here. So there's another property that we can use. That is to negate, okay, the value that is the whole integral expression. I shouldn't say value, I should say expression. So that I can flip the upper and lower limits of integration. So I'm negating this. I'm going to actually bring the negative in front of here. So I'm going to, that's a negative. Change the color a bit so we can see how strongly that is before we switch. Now the A is at the bottom, which is precisely where we wanted it to be. Now, there's another little issue that we have that we didn't have before, and that is, okay, not that A isn't at the bottom because now we have A at the bottom, or that there were 2 of them from the beginning with X's, but rather that it's not just X, okay? In this case, it's X squared, and in this case, it's X cubed. Okay, so what we do is something called U substitution, okay? So in this particular instance, I'm going to make U X squared, and I need to find the derivative of U. All right, du is 2x, all right? You can write the dx, you don't need to. If you've heard of this strategy before, maybe in a physics class. Now, in this case, you can use another u. You can also just make sure that they're separated if you do. I can use the letter v. I'm just going to stick to u because I feel like it's very clear as to where it's going for each. So derivative of x cubed is 3x squared. So once again, why we did this is because the upper limits of integration were not just x. Okay, so if you're going to differentiate and it's not just x, you have what is called the chain rule. So you may have noticed this in the slide. I said with chain rule, that's kind of where this is coming into play. So let's go to a step 4. Okay. Step 4, I'm going to say some of this work for the U substitution. All right. Okay. So U substitution. Now, you don't have to label these steps. As I showed you, there's like more than one step in 2. I just want you to clearly see what we're doing because it's not as straightforward as example 1. And I don't want to lose anybody, okay? So I'm just rewriting from what we have below. And the dx is actually going to become du. And we're going to say from a to u. And it's still the cosine of 2t dt. And d over du, whoops, the integral from a to u, cosine of 2t dt. Okay? Now, we need the du there in order to actually undo this part. But what's happening is if I'm just replacing dx with du, okay, I'm going to come down over here. Du over dx is this. So I need to actually multiply 2x with this expression. So I'm rewriting step 4. And I know I'm probably going to run out of space. But hopefully, if you remember with the chain rule, that ends up happening. Remember, dy over dx is dy over du times du over dx. So that's what we kind of need to establish here. Before we undo everything. Okay? And you can see, you guys know how to cancel factors. You can see how that cancels. So you're getting what you originally had over here and here. Okay? So next step is to plug in. Use the fundamental theorem of calculus. So that's kind of squishing in here. dy over dx is going to be 2x times a negative. Remember, this undoes each other. We're going to plug the u in. That's the fundamental theorem of calculus. And, or that's a times. Over here, du over dx, I didn't do it here, okay, is 3x squared. And we're going to multiply it. Remember, this kind of undoes each other. Cosine of 2u, okay? And now we have to replace the proper u's, and then we're done. So let me go back 6, really squeezing it in here. This is 2x, and I'm multiplying by a negative cosine of 2. This u is x squared. And this u is x cubed. So my final answer, dy over dx, just kind of neatening up from step 6, is negative 2x cosine of 2x squared plus 3x squared cosine of 2x cubed. Okay, and then that's it. Okay, this is our end answer, so I'm going to try to box this. And I know I said that's it, that wasn't a lot of work, but we went over a lot of things like the properties and fundamental theorem of calculus and chain rules, so it's a lot of review in this problem too. So take your time when you do this, and good luck.